Hey you guys, welcome back to the channel PHYSICSSIRJEE, and here we are in Resolved series in which I brought forward to you a situation that is very interesting at the JEE level. And during the course of solving this problem, where we have a current carrying wire, as you could see on the thumbnail, where current is changing with time. It could be increasing or decreasing, and we all already know what is the direction of the magnetic field in the vicinity of the wire. But the idea is to get the direction of the induced electric field due to the time varying magnetic field. So as we solve the problem, we'll also see the importance of the idea of curl of electric field at JEE level. I know a lot of students at JEE level generally fear this idea of curl and divergence, but we'll try our best within the confines of the syllabus to visualize and compare it with fluid situations also, and we'll be able to get the concept right. As usual, at the end of the video, we'll top it off with two practice problems pertaining to the concepts that we learn from this particular video. Okay, so let's move forward. I'll present to you the statement first. Yeah. So a long straight wire carries a current that decreases linearly with time. Right here, what is the direction of the induced electric field outside the wire? Is it parallel to the current, opposite to the current? Is it pointing radially outward from the wire, pointing radially inward, or idea is whether there is no electric field induced outside the wire? So try to pause the video, try to think, use your right hand thumb rules and etc, all these Lenz laws that you have studied in your school section, and try to come up with an answer within 1 or 2 minutes. But also let's try to see the concept that is involved, and we'll try to get to the answer and also top it off with the practice problems after comparing this situation with fluid mechanics. So in the course, we'll try our best to visualize the curl idea. Okay, so before I move forward to develop the video, as usual, a humble request, 60 likes for this video will immediately trigger the upload of the next video, or we'll wait for the 10 days, as is the case with the last video. I think I have promised that 600 likes did not reach, so I come up with the video within 10 days. So I hope you support this and ensure that the channel keeps itself alive. Okay, so let's move forward. And for those who are beginners in this particular channel, to understand the induced electric field in time varying magnetic field, I have produced two videos last year which are very well appreciated and wholesome, in a sense that they cover the complete postmortem of that concept. So I've presented to you the thumbnails of those videos on the screen. The links of these videos are in the description below. First one is complete postmortem of the topic, and the second one contains the practice problem solutions that were presented in the first video. Okay, so please do check them out, and in case you find them really good, try to comment below those videos about the understanding, and also maybe in case you have the doubts. So for those who watch those videos, a very quick concept that we understand in the time varying magnetic field: whenever there is an increasing or a decreasing magnetic field, there is an induced electric field which is created like a vortex, or you could say curling field, that would be around the increasing magnetic field. Okay, so how to check whether this induced electric field exists or not? You can place a material ring and place a galvanometer or something and measure the direction of current or induced current magnitude in order to substantiate the idea that this electric field gets produced whenever there is a time varying magnetic field. Here I have shown an example of increasing B, right? Increasing B. So there are increases of flux in this particular region, and because of the right hand thumb rule and the Lenz law, the direction of the induced electric field produces the current. Okay, so that was the concept we learned from that old video. Now let's try to take it a bit further. And I know a lot of stuff on this particular screen is intimidating, but try to hold my hand and we'll try our best to get the idea. We're not doing the rigorous math here. Okay. So whenever we write the Faraday's law at our JEE level, we write it in an integral form. So at slightly higher level, we can use Stokes theorem in order to convert this integral form of Faraday's law, where induced EMF is rate of change of magnetic flux. Okay, so you could see in the first line, you can convert that into a curl operator like this. Okay, so you'll be learning this type of conversion from a aerial flux to a curl of field along that particular area vector here. Okay, so in this del cross E, when you try to equate it to the rate of change of magnetic flux, you'll end up getting the differential form of Faraday's law. Okay, why we wrote this is we're not going to do the rigorous math, but we'll try to generate the direction of the induced electric field in case of a time varying magnetic field. Imagine this time varying magnetic field is not varying super fast. So whenever there is no super fast variation, we can still apply Biot-Savart law. In reality, Biot-Savart law is only valid for steady currents. But if the variations are small, we can make an assumption and we can assume that the Biot-Savart law is valid. So imagine if it is taken for a small current carrying element, then you would use that B as this number. Now here comes the magic or the symmetry analysis. Whenever you have a del cross E on this side and ideal bar cross R bar, the idea of the mathematics reveals itself and produces a simplistic situation of E bar being along this ideal bar because of the cross products involved. Okay, so let me further analyze that. So assuming Biot-Savart law is valid, the last step of the previous slide, I borrowed it here. I'll try to take you into a situation of a symmetric understanding where if you are looking at a solenoid and current is curling like this in one particular sense, right? You could see the current from the actual view. We already know from the old videos how the direction of the induced field exists. Okay, and you realize in that whenever there is a cylindrical symmetry involved, the direction of the electric field in the wire and the direction of the current which was originally responsible for producing it will be either parallel or anti-parallel. Okay, so what I mean to again say is, because of the way you are going to write this curl in the cylindrical coordinate system and being equated to this ideal bar cross R bar, it comes out in mathematical symmetry that the direction of this E bar will be along the direction of ideal bar. And you could see that in our favorite example, where the current, if it is in the clockwise sense, it produces a time varying magnetic flux or time varying magnetic field, and then in a ring that is present outside there will be a induced current or induced EMF which would be in the same sense or the opposite sense. It will be along, as you could call it, in the direction of the original current. So that is what I have written at the bottom, which we'll use to solve the problem. So because of the curl on the LHS here and the cross product involved in the RHS here, wherever there is a cylindrical symmetry, the shape of induced EMF E lines match with the physical shape of the current carrying wires. So in the present example on the board, I have taken a past solved problem where if the current is curling like this in a tangential manner, then the field is also in a tangential manner. Whereas in the current problem, we have a current moving in straight line. Okay, so let's try to see. Okay, so again, the same thing I have reiterated here, right? So if the current is in a tangential manner, then the electric field induced also would be in a tangential manner. And if current is increasing, then we will end up getting E and I to be in anti-parallel direction. If current is decreasing, they will be in parallel direction in case of a cylindrical symmetry. Okay, so now try to apply that symmetry argument using that curl for the long straight wire situation. So using a right hand thumb rule, the magnetic field lines are in this manner. So if I use that understanding that, let's say, let's try to talk in general, if current was increasing, then it would have produced a magnetic field which will be decreasing. And we already know induced electric field should be such that the current produced in this loop that is placed here should try to improve oppose the increasing magnetic field. When is this possible? It is possible if this increasing current produces a induced electric field which is anti-parallel to it outside, and that too it should not have a uniform value. It should be in this manner so that the free charges in this would be moved in such a way in order to produce the current. Okay, so this is the direction of the induced E bar that we are trying to think of in case of an increasing current. So I know the original question was about decreasing current, but this I'm trying to reiterate as an example. Okay, so same thing here. We're trying to look into this thickness of the wire here. So imagine this wire has been drawn in a horizontal manner and the current is going through its cross section. The magnetic field lines will cut through the flux here in this region and produces a induced electric field. If current is increasing, this induced E star should be in anti-parallel direction. Not just outside that is asked in the question. If you even think the direction of the E star in the inside part of the wire, you should visualize this E star's role is to oppose the increase in the value of current. So by producing a green color E star in this manner, you could visualize that it is trying to decrease the direction of or magnitude of the current. By for chance, if the value of I was decreasing, like in our problem, this E star's direction should be in the rightward direction. So parallel or anti-parallel, it should be along the direction is what our answer is. So let's try to answer it and then move into the bonus facts. So for this current problem, because in the question he is given decreases linearly with time, you should say it should be parallel to the current. Okay, so I hope you understood the problem up till here and you're excited to move on to the comparison between the curl of electric field in this topic to the curl of velocity in a fluid dynamic situation. That's how the word curl operator comes into picture. The idea of the English meaning of curl is whenever there is a kind of a rotational effect that is created by any field. Okay, so imagine you are having a river in which velocity field vector or velocity vector of the particle of the streams of the flow is given by certain function. So in the left side of your picture, you could see I've taken certain function where the river is flowing and these are the two banks of the river. And I have taken a practical situation where river might flow faster in the middle and slower at the edges. So I've taken a simple parabolic variation. So now if you apply a curl for this velocity function, you'll end up getting it is non-zero. This kind of non-zero curl represents a rotational flow in fluids. So how do you visualize this curl? If I have placed a small floating disk in the stream of this river somewhere here or on the right side. So let's take the example of the disk that was placed here. The left side part of these stream velocities and the right side part of these stream velocities would be unequal to each other in this non-zero curl. And because of that, there will be a rotational effect that would be produced with respect to center of mass for the disk. So if you closely observe the video of this slide, you would see that the disk actually rotates anti-clockwise when it is kept here. Whereas simultaneously, if the disk is kept in this position, because this side the velocities are stronger as compared to this, the disk will tend to have a rotation in a clockwise sense. So this is a very beautiful video from Open University from which I have picked up these pictures. So link of that reference video is posted in the description below, which gives you a nice insight into the idea of the curl being non-zero in fluid flow. And that's how the word English word for the operator comes into picture. Now let's try to use this visualization for the current problem, wherein just like when the curl was non-zero in case of the liquid flow, we ended up having a macroscopic rotation of an object. Similarly, whenever the B was increasing in front of a straight wire, the value of the curl of E doesn't come out to be zero, right? So it's a non-conservative electric field. Whenever curl is non-zero, it's a non-conservative electric field. I know here when you place the loop, you don't see a macroscopic rotation, but these, because there is no net charge on the loop, so center of mass of the loop doesn't move. But at the microscopic level, the free charges that are there inside, obviously the free electrons, would be unequally forced on this side and this side, because of which there will be a net rotational effect or microscopic rotational effect of free electrons in the loop, causing the induced current. Here we have shown the direction of the conventional current. If you look at the free electrons motion, it would be exactly in the reverse sense. Okay, so this is the visualization that you should have. Imagine the curl of E was not zero in this case. I'll give you a simplistic example. If the electric field was uniform, that's a special case of curl being zero. Okay, in the electrostatic field, in such conservative electric field, the electrons here and here would be pushed equally, and you will not get this rotational effect, thereby saying that there won't be any induced current in a conservative electric field situation. So this non-conservativeness is the requirement for the production of this induced current. Okay, so now the bonus point too, this is even more interesting and even more practical. How are the EM waves produced from an antenna rod? An antenna rod is like a straight conducting wire carrying current, but there the current will be actually changing with time. So just like our problem, which I have drawn on the right side, when the current, let's say, is linearly increasing, imagine there is a linear increase, the direction of the field will be parallel, and this electric field, if I had draw a graph with respect to position, I'll end up getting a linear sense. So you can also further think that whatever is the function of time of current, that shape of electric field produced also will be of a similar kind. So in real life, whenever the current is not actually linearly or increasing or decreasing, but sinusoidally varying, it produces an electric field in front of that wire. So imagine this wire has a current which is sinusoidally varying, oscillating. I'll show you a video of that. And then it produces an electric field which is either parallel when it is decreasing, or anti-parallel when it is increasing. Okay, so and I have drawn two parts up till t/4 time period and t/2, wherein you could see that these produced electric field will travel in the rightward direction along with the magnetic field that is produced. So I'll show two parts of this video in which you could see that electric wire is in the straight y direction. Imagine y direction, right? And in this picture, I have not shown the magnetic field. Magnetic field will be into the board, and electric field which is induced, that is produced, is moving in the pair plane of the paper. Okay, so the shape of this electric field function is decided by the shape of the variation of the current. And you could see why sinusoidal production is easier as compared to a continuously increasing function. Sustaining such increasing currents would be difficult in a wire, whereas increasing and decreasing the currents and producing sinusoidal currents would be easier, and thereby traveling the electric field. Okay, so let me show you a part of that. So this is how a dipole antenna works, in which you could see, I'll try to slow down the video a bit. Okay, so right now you could see the current, whenever it is increasing or decreasing, it's producing an electric field which is parallel or anti-parallel. Whenever it is increasing, you could see right now the current is shown to be very small here, and the green color arrows which represent the induced electric field are anti-parallel. So whereas once they are decreasing, right now in the decreasing form, the currents and the electric fields are parallel to each other. And as the time progresses, these sinusoidal variations will be produced in space, and they'll be sent in space. In this particular picture, I have not yet drawn the magnetic field. There exists a magnetic field also using right hand thumb rule, perpendicular to the direction of travel and also the electric field. So let's try to see a situation where I'll try to slow down this video. So for those who want to just watch this by pausing the video, you can use that. Okay, so you could nicely see where the current direction and the electric field produced induced wise are parallel or anti-parallel and nicely moving in a sinusoidal manner. So, but if I also include magnetic field in this particular video, you'll end up having the electromagnetic wave production, which now you should understand how it is visualized. Okay, so shall we add that? And I'll try to make this wire along the y-axis so that it's easier for us to visualize. In the new video, you will not have the wire. I'll remove the wire because it will become very bulky, right? So this is how it should look like. So imagine the wire is along y-axis. So therefore, electric fields are produced along y-axis and sinusoidally varying, and the magnetic field included is in the z direction, and the direction of propagation is in the x. This is how your EM waves are produced and received by antennas. Okay, so the basic understanding of this question takes us more into a journey of understanding the practical EM waves production. Okay, also solving the JEE advanced question that I have posted at the start. Okay, so apart from the Discord server, Telegram, and website, there is also social media presence for this particular channel. So all of these links that you want to explore are in the About Me section of this channel. So please do help yourself. And regarding the website, there are videos. I'm updating them as soon as possible. So those things are arranged in a chapterized manner in the problem set. So how to use the website, I've already made a tutorial video. The link of that is in the description below or I button above. You can check it out if you are new. And these are the practice problems. The first one I picked from Pathfinder in the objective section. So how to use this idea and visualization of the curl? You have multiple ways of solving the problem, but I would like to the students to have an understanding of how this electric field is produced and use it to solve this problem in a slightly shorter steps without using integration. Okay, so that's the expectation from this JEE advanced level question. Practice problem 2, slightly more difficult, from Build Up Your Understanding EMI chapter. Okay, so there will be a sudden switch off of electric field. So there will be a impulsive induced electric field which causes some momentum for this particular loop. So let's try to see how many of you get this one right. Whether you can use the present video solution or you have to use some other method, please try to comment your response below along with the timestamp. Timestamp helps me navigate the doubts easily once the old video becomes old. Okay, and in case you want to have more topics covered, electrostatics, electromagnetics, etc., all the subtopic playlists are taken up and put in the description below, so please try to explore them. Regarding the Discord server, how to use our Discord server and how to use the electromagnetism channel separately present where the students are discussing great number of doubts. I have made a video tutorial on the usage. Try to check that one out. Link of that video is in the description below or I button above. Right. So please help yourself. Apart from the result series, this channel contains many other important series. I've written only 4 here. There are many more which help the students. So links of all those important playlists are in the description below. You can also go to the direct playlist section of the channel and explore it all by yourself. So likes are important. So please, I request you again and again so that the likes target is reached and I upload the immediately the next video. And please do share and subscribe to my channel in case you didn't. Hit the bell notification bell icon because I keep regularly putting up the community posts of important channels. You'll end up getting the notifications immediately when I upload them. Okay, thanks for staying this long and see you in the next video.